In this and the following segments, we'll look at using subqueries within larger queries. This is one of the most powerful SQL features. In this segment, we'll go over single-value subqueries. So far, we've seen two examples of using a query as a source of data within a larger SQL statement: the insert into select statement, and the use of a select within an update as the right-hand side of an assignment. Review those two cases if you need to. They were in the discussion on altering databases. SQL allows much wider use of subqueries, select queries within larger statements, than just those two examples. It's not too much of an exaggeration to say that almost anywhere a single value is needed, in a where clause for testing, in an update assignment, even as columns in a select clause, you may substitute with a parenthesized select statement that produces a single value. And a select that produces a multi-column result may be used almost anywhere a table is expected, in a from clause, as a participant in a join, etc. In the following discussion, we'll look closely at examples of these cases and more. We'll use the bakery4.sql and courses2.sql files supplied. Be sure to load them instead of earlier versions, as they include some extra rows useful to this discussion. Let's start with the uses of subqueries as single values, or scalars, in various contexts. We already know, for instance, that we may use a subquery on the right-hand side of an assignment in an update statement. Review the earlier discussion on this, and then try this first question. We have in the Courses2 database a term table. Let's assume we alter that by adding a column num sections to that database with the altered table statement there. And your question then is to write and test an update statement that sets num sections to the number of sections actually offered in each term, as indicated by the number of section rows for that term. You'll need one simple query as the right-hand side of an assignment using an aggregation function. And so coming back from a pause there, what I came up with was to update terms, set num sections equal, and then there's a count of the relevant sections as a subquery, assigning that value to num sections in each term row. And there we go. To a rough approximation, a one-result query is simply an elaborate sub-expression. You can combine it with other operands and use it as part of larger expressions in any context that a value is needed. You do need to parenthesize it. A select is, in effect, a lower precedence operation, so it requires parenthesizing. Now, for instance, you can use single-value queries in the select list of a larger query. Perhaps we want to select for each course the course ID and number of sections offered of that course across all terms. This query here will do that. So what we will do is select ID and then a sub-expression that selects the count of sections for that ID as a sub-value in the select list. And running that, I get a nice list of ID and number of sections of each, course ID and number of sections for each. Note, by the way, that the subquery here is renamed as sections. Absent the rename, the query itself becomes the column title, which isn't very nice looking, so we have sections there instead. And note also that we used course.id within the subquery, and that references a table from outside the subquery. Select from course. The subquery assumes that unqualified column names refer to the tables in its from clause, section in this case, for instance, if possible. So for now, qualify any out-of-subquery column with the table name, and we'll look more at this issue shortly. So moving on to question 2, try running a query that lists for each customer in Bakery2 the first name, last name, and a total of all purchases that she or he has made with the column header Purchases. Now do this entirely by a subquery in select, rather like the one we just did, and that subquery may have a join of just 3 tables. Your full query must end with from customer. Coming back from a pause there, this is what I got. the subquery joins receipt, line item, and product to get a sum of purchases for each customer. The outer query supplies the customer.id, so there's no need to mention table customer specifically in the inner query. You may also have noticed that this query does the same thing we did without subqueries in the earlier discussion on group by. Subqueries can often be avoided with clever use of joins and grouping. We'll talk more about the trade-offs in a bit. Now, single-value subqueries may also appear in the where clause as sub-expressions, and this is perhaps their most common use. Any place you can use a column name or a constant value in a where clause, you can insert a parenthesized single-value subquery. So here's a query, for instance, to give a first and last for all customers with more than $100 in purchases. So running it, we see we have these 8 customers. And tearing that apart a bit, you can see that we are comparing the customer where the sum of all prices from receipts joining line items joining products is greater than 100. So this entire select here from there to there is producing a result against which we're comparing with 100. So using that as an example, write a query that gives the first and last name for the customer with the highest ID number in the customer table. Coming back from a pause there, this is what you might have come up with. Select first name, last name from customer, and again the where clause uses a rather simpler subquery. Just select max ID from customer. Compares the ID for equality with that, and we get Stephen Zeem. So let's try something more interesting here. Compute for each customer the spread between their most and least expensive purchase. This might give us some sense of whether people tend to stick with high-end or low-end products. List the customer first and last name and the price spread. Omit those with no purchases at all, and sort in descending order of most expensive purchase. Now, we're going to do this in stages. First, just list the first name and the last name and the highest purchase price for each customer in descending order of highest purchase. Use a reasonable column header for that highest price. And in the order by clause, remember that a column header is also a rename. So, coming back from a pause there, this is what I got. Select first name, last name, and then a subquery for the maximum price in the select clause here. And we'll select max price from receipt, joining line item and product appropriately in customer ID, and call that max. And then we'll select all that from customer, and we'll order by max in descending order. And we'll get the following. Note, by the way, that the Bakery 4 database supplied for this lecture has at least one customer with no purchases. That would be Joe Cheap down here. Numerical aggregation functions, like sum or max, return null when they have no data to work on. So let's move on now to question 5. We want to extend this to the full specification from earlier. A spread for all customers that have at least one purchase, and in order descending by maximum price. So you're going to need 3 subqueries. Put one in the select to compute the spread, use one in the where to filter out the customers with no purchases, and use one in order by for the sorting by max. Coming back from a pause there, I came up with the following here. Select first name and last name, and then a subquery in the select that is similar to the one from max in question 4, but we've expanded it to compute the spread between max and minimum price. And we have a subquery to count receipts in the where clause, and to make sure that that's greater than 0 so we can filter out Joe Cheap and his ilk. And then finally there is a subquery in the order by clause, which is just like the max subquery for question 4. And there's the rest of that one, sorry. Okay, running that, and we get the desired listing. Now, you might, by the way, have been tempted to try to filter out Joe Cheap via where spread is null. That's a clever idea, but it won't work. for reasons we'll discuss in a bit. So, to that end, let's talk about some limits and special considerations. There are several traps or limitations to bear in mind regarding single-value subqueries. First, the scope of column names. The scope of column names, which table they belong to, comes up often in subqueries, and it's a common source of bugs. Let's try something here. We'll run the following to list course ID and number of related sections for all courses using the Courses 2 database. And that's the query I want to do. It's reasonable enough. Select count star from section where course ID is ID from course. Okay. But when we run it, we find out it results in a listing with just one section per course. And that's clearly wrong. This happens because the comparison course ID equals ID up here compares each section's course ID with the ID of that section. And that's meaningless. It turns out that only one section has such a match, and that's why the subquery returns just one. What we wanted, of course, was to compare course ID with course.id, thus, and this gives the expected result. Any unqualified column name within a subquery is taken from the tables referenced in the from clause of that subquery, unless there are no matching columns, in which case the unqualified column is assumed to be from tables in the outer query. In extreme cases, subqueries may be nested inside of other subqueries, and the general rule is that the column name, absent qualification, is taken from the innermost subquery for which there is a matching column in the from clause. In the tables in that from clause, that is, in a manner similar to variable scoping in a language like JS or C, where a variable name is first a local variable and then a global variable, and so on. Now, the second limitation is that you have to filter selected subqueries via having, that's subqueries within the select clause, via having, not via where. So, for instance, here's a query that putatively lists ID and a count of corresponding sections for all courses having a section count larger than 3. So we have a select there of section counts, and we're checking to see if it's greater than 3. But as you can see there, it gives an error that scount is unknown in the where clause. The fix is to replace where with having instead. Thus. So, question 6, why does that change fix the problem? Think about it for a bit. And coming back from a pause there, remember that where is performed before the construction of the select arguments, and having is performed on the result of the select arguments. So to use a subquery from the select clause as a row filter, you must use having. The subqueries in the select have not been performed yet when where is executed. So question 7, using this new information, improve my answer for question 5 to get rid of the second subquery by using spread instead. Coming back from a pause there, I got the following, which as you can see is like the answer I had for question 5, except that it uses a having spread is not null, which before we said would not work, but with a having, of course, it will. So running that, we see that we get the expected result. And then a final, small but important restriction. A subquery in an update may not make use of the table being updated. For instance, say we wanted to take each product in Bakery 2 and assign it a price that's equal to the max of all prices. I'd be tempted perhaps to write something like Bakery 4, I should have said, sorry. Select product, or update product, set price equal to select max price from product. Straightforward enough, but no. And the reason it's rejected is because the update statement doesn't permit use of the target table product in the subquery, since the very table being subqueried would be a moving target as row by row is updated. So although this particular update statement is actually unambiguous, The possibility for ambiguity with such usage is too great. Imagine, for instance, adding 1 to the result of the subquery, select max price plus 1 from product, in an attempt to make every price 1 greater than the maximum. That couldn't possibly make sense.